Okay, great, thanks. And thanks, of course, for the opportunity to speak to you all today. I guess what Andy had asked me to focus on was looking at applications of remote sensing data. And we have a program of mapping that I'll introduce in just a minute, so I'm going to just quickly introduce that, run through all of the different bits of information that we're extracting from the data, and then wrap up with some new R&D activities that we have using those pieces of data. Let's see if I can get this to go. So we have a national coastal mapping program with the Corps of Engineers, so we're looking at remote sensing data from an engineering perspective. So we want to collect high resolution, high accuracy elevation and imagery data around the coast of the U.S. on a repeat basis. So not just one time, but repetitive, so that we can understand how the coastal zone is changing, so that we manage our projects in concert with natural processes as opposed to against them. So we use this data to manage our projects as well as manage projects on a regional scale. The image in the background is some data that we collected in Hawaii back in 2013, but what's important here is the arrow, which shows our collection scheme. We collect about 500 meters of topographic LiDAR at the same time that we're collecting 1,000 meters offshore with bathymetric LiDAR. And I have some more examples of that in just a minute. But what we're trying to do is capture the active part of the beach profile, so where all of our sediments are moving, because our focus is on sediment management. This is a graphic that shows our progress to date. We started in the Gulf Coast back in 2004, and we've gone around the coast completely one time and almost finished our second cycle. And as the program's gone on, we've developed a suite of kind of basic information products, and I'll just let you read those that we produce from the data sets. Again, it's the Bathy LiDAR, Topo LiDAR, aerial photography, and hyperspectral imagery. And then I guess in the past 3 years or so, we've looked at some newer products or newer pieces of information that we're extracting from the data, and I'll go through those in a minute. So just to show you some examples of the data, this is from Lake Ontario. This is actually some older data that we collected back in 2007, but this is on the bottom half of the slide we have topographic LiDAR. The top half of the slide is bathymetric LiDAR, and you can see the irregularities in the topo LiDAR surface. The buildings and the trees and all of those resources are still in this image, and we run some automated extraction techniques to take those out so that it exposes the hydrology underneath. And this is the type of product that our hydrodynamic modelers use when they're looking at flood modeling, is that digital elevation model or bare earth surface. We produce something called a laser reflectance image. We have a radiometrically calibrated laser sensor. This is an example from California back in 2009. The top part of the screen is the topographic LiDAR, and the bottom, or is land, and the bottom half is water. And you can see these striations here in the offshore, some kelp beds. So using information out of the Bathy LiDAR, we can look at reflectivity of both the land and underwater surface, and that helps us understand what the benthic habitat type of information might be, as well as the land. We're also collecting aerial photography. Bathy LiDARs fly lower than topo LiDARs and traditional aerial cameras, so we get very high resolution imagery at our 400 meter altitude. This is about 5 centimeter resolution imagery that we're collecting at the same time as the Bathy and topo LiDAR. And we also collect hyperspectral imagery using a CASI 1500. It's a programmable sensor, so we're able to there's a trade-off, I guess, between spatial and spectral resolution, and we've settled on kind of a middle ground for both of those, where we collect 1 meter pixels of hyperspectral imagery with 48 spectral bands in those. This is an example from Port Susan Bay in Washington State, Puget Sound, that we collected in 2014. I mentioned that we're looking at change with our repeat data that we have all around the coast of the U.S. One of our products that we're kind of moving into standard production is a volume change, or looking at the change along the coast. And we kind of isolate that to the sandy part of the shoreline. And this is an example of some data or a comparison that we did, I guess it was from about 2010 to 2012. So we collected after Hurricane Sandy some post-storm data, compared it to our pre-storm data set, and produce an elevation change map. So that's what you're seeing here in this little tiny strip of brown and blue. on the slide. So brown is erosion and blue is accretion, and then we have the little boxes on the outside, so you can click the box and see what the volume change was in each of those, and we're producing that for most of for our coastline in the Gulf Coast and the Atlantic Coast right now. Other information that you can extract from these data sets, we're interested in looking at our dune system that provides some protection to infrastructure behind it, as well as critical habitats. So we cut cross sections from onshore into offshore, so you're looking at elevation cross section and looking at the inflection points on those. We can locate the dune and find the height of the dune as well as the toe of the dune, looking at our offshore bars, and we can plot those dune locations in a geographic sense, or we can look at what I've called spaghetti plots of dune height, so how the dune height changes along shore. In this case, our average dune height is somewhere in the neighborhood of 2 meters, and you can see the variability goes from about 1 to 3 meters in this particular section of coast. We look at a zero contour. Shoreline is kind of a loaded word in the U.S., so we just say zero contour. This is our NAVD 88 shoreline. And so you can see over on the right-hand side of the slide how our shoreline has changed from 2004 to 2010. Again, looking at it in the along-shore sense. You can see the variability along-shore and then also what the amount of change is. And then we also compute a beach width, so that's the distance from the shoreline to the toe of the dune, and you can see how that changes for this section of coast. I should say our test area that we're working in is the Gulf Coast of Florida, just to orient you in space a little bit, so you can see that here. Sarasota, Tampa Bay is up there if you're familiar at all with the area. The Corps of Engineers is interested in looking at inlets and the infrastructure around them. We're responsible for maintaining navigation channels to support commerce in the U.S. So this is one of our navigation channels down in Florida, and what we're able to do is compare successive surveys in those navigation channels and establish shoaling rates. So where is sand gathering the most in the channel? So these areas that are red have high shoaling rates relative to the blue ones, and we are also looking at these shoal features in the offshore. I guess the amount of volume change in those shoals has some impact on the adjacent beaches, or means something in terms of the health of the adjacent beaches. So we're able to automatically identify the location of these shoals as well as compute the volume change through time. For our coastal structures, and I have a lot of these cross sections, so I'll just start scrolling through them. We're looking at them in terms of asset management and the health of our coastal structures. So what we're able to do is cut cross sections or profiles along these structures and see how they change through time. We've got 3 lines on each of these plots that shows the 3 different years of surveys that we've done at this Hampton Harbor, New Hampshire navigation project. Keep scrolling, I don't want to go too fast, but you can see how the structure changes through time, and we use this to determine where we might want to focus some of our efforts. In a similar way, this is just another way to display similar data. So we're looking at the volume of the structure above the water line versus below the water line, so we're able to see how that changes through time and understand where we might want to focus some of our management activities as we scroll through these. Using the LiDAR data in combination with the hyperspectral imagery, we're able to do some interesting classifications and start looking at some of our environmental resources. We're able to locate the dune based on the LiDAR data elevations, and then using hyperspectral imagery identify which pixels in that dune location are vegetated, so that we can start to understand what the density of vegetation on the dunes is. And again, that's important for our critical habitat as well as the stability of the dunes in the face of our storms. And we're also able to look, I showed the graphic from California earlier with the kelp beds, but this is another example of using the fused LiDAR and hyperspectral imagery to look at submerged aquatic vegetation. This particular project was actually looking at discriminating macroalgae from eelgrass using a combination of the LiDAR and hyperspectral. And this, on the bottom of the slide, are all of the different products that we can extract using a technique called spectral optimization. So you can even get information like, what, did I mess something up? Color dissolved organic matter concentration, as well as chlorophyll concentration, in addition to the reflectants and other products. I think I exited myself from the, there we go. And the way we've been using these parameters in R&D, there's a list on the bottom, and I'll go through a few of them in just a minute, but we start out with our elevation and imagery data at the top, extract the different parameters that I just mentioned, look at some land characterization techniques, and then bring them into some of our R&D. One of the first things we try to do, again, this is going back about 3 years, and we're working on refining this and what it needs to look like, is to develop a set of stoplight indicators to help the management community. So for people that don't understand the data or have a lot of capability to work with the data, we're working on a product like this that takes some of our parameters and puts it in a digestible form. So we have a geomorphology index, and where you have a green spot at that particular location on the shoreline, the dune is high, the beach is wide, and the shoreline's not changing very much. If you're in one of the red zones, that means the dune is low, the beach is narrow, and you have an erosive shoreline. This second index is what we've called environmental index, and where you have a green spot, that section of the shoreline has a high concentration of environmental resources. So in this case, we were looking at wetlands, the dune vegetation that I showed earlier, and the submerged aquatic vegetation. Our human use index is looking at impervious surfaces, so how much infrastructure is in a particular area of the coast, and you can see it's mostly green because this part of the coast is fairly evenly developed, and these right now, these are kind of relative metrics. What we want to do in the future is develop some metrics that we can use nationwide so we can start comparing different sections of the coast. And then the pie charts are related to our navigation features, so we're looking at the navigation channels, if they're open for navigation, a certain percent. Our ebb shoal stability, the volume of those shoals, is it changing a lot or pretty stable? And then structure integrity, how well do our navigation structures match their design profiles?